Hello everyone. Today I will do one more example about shear force and bending moment diagram. Let's take a look at this beam here. There's a pin support and a roller support, and there are two kinds of loads, distributed load and concentrated load. So let's get started by drawing the free body diagram of the beam. You see that there are two reactions at point A and one reaction at point B. And from the free body diagram, we see that there are three reactions, and we have three equations. Since E equal to R, it's a statically determinate structure. Before I start calculating reactions at the supports, let me convert this distributed load to concentrated load. And we know the area of the distributed load is equal to the concentrated load. So the area of this triangle is equal 100 kilonewton. And from the properties of the triangles, this distance is equal to 2/3 of the whole distance, which is 10 in this case. And this distance is equal to 1/3 of the whole distance, which is 10 in this case. Now let's take the summation of moment about point A, and I will take positive is clockwise. There is minus 10 by plus 100 multiplied by 2/3 of 10 plus 50 multiplied by 15 equals to 0. This 2/3 of 10 is the distance from point A to the 100. Solving for By equals to 141.7 kilonewton, and our assumption is correct. Now let's take the summation of forces on the y-axis. There is plus AY minus 100 plus 141.7 minus 50 equals to 0. Solving for AY equals to 8.3 kilonewton, and our assumption is correct. Since there is no loads on the x-axis, so AX is equals to 0. Now we have all the reactions, so we are ready to draw the shear force diagram. Now let's draw the shear force diagram. At this point, we have the reaction AY equals to 8.3 positive. So we go up 8.3 kilonewton. Now we have a distributed load here going downward. So we need to go down by the area of this triangle, which is 100. So 8.3 minus 100 is equal to minus 91.7. And the shape here will be a curve like this. At point B, there is a reaction By equals to 141.7 kilonewton. So minus 91.7 plus 141.7 is equal to 50. So we go up until we get to the 50 kilonewton. Now since there is no loads, no effect, so straight line, and finally we have minus 50, so we go down by 50 until we get to the 0. The shear force diagram closed at 0, which is correct. Before we start drawing the moment diagram, let's find this distance, x first, where the shear equals to 0. We can't use the similar triangles to find x in this case, because these are not actual triangles. You see, this is a curve, so these are not triangles. So we will cut this section and this point and find x where the shear equals to 0. And this load is W in this case, not 20. So we need to find W first. If we cut this section, we will have the following shape. So this is our section, this is W here, and here the shear equals to 0, as we said. Let's find W first. By similar triangles, we can find W. This gives us W equals to 2x. So this here is 2x. Now we can find x since it's the only unknown on the y-axis. So by taking the summation of forces on the y-axis, we will find x. Solving for x equals to 2.9 meter. To draw the moment diagram, there are many methods. One method is to calculate the area under the shear, which equals to the moment, or you take sections throughout the beams and calculate moments. I will use the section method in this example. So we need to take sections on the beam where there are loads and reactions and zero shear. The section of the zero shear is ready here. Let me first convert this load to concentrated load, as we did before. So this x is no longer unknown. It's 2.9. So we can calculate the area of this triangle, which equals to 8.41 kilonewton. Now let's find the moment. Solving for m equals to 16 kilonewton meter. So at the zero shear point, the moment is 16 kilonewton meter. And we will have a curve here. Now let's take a section at point B. So this is section AB. And let's convert this distributed load to concentrated. So it's 100 kilonewton. If we take the moment about point B, we will have the following equation. Solving for m equals to minus 250.3 kilonewton meter. So the moment at point B is minus 250.3. And the shape here will be a curve. Now let's take the last section where we have 50 kilonewton concentrated load. The moment in segment BC is equal to 0 because this force, 50 kilonewton, has no effect since we are calculating the moment at this point. So the arm is 0, so the moment is 0. Finally, the moment at this point is 0. And because we have a rectangle here, this will be increasing slope because this area here is positive. That's it. Thanks for watching.